Welcome to Unit 6, Inference for Categorical Data, Proportions. In this video, we will be talking about Topic 6.2, Constructing a Confidence Interval for a Population Proportion. All right, guys, this is a super important video moving forward. It's going to be kind of a longer one and a really important topic that if you could grasp it now, it'll actually make a lot of things down the line a lot easier. So there's a lot of writing and a lot of explanation in this video. I'm going to do my best to explain it all, but this is one of those videos where it couldn't hurt to do a little bit of pausing every now and then, reading what it says, and then listening to what I say to try to really fully grasp all of the tiny details. But I'll do my absolute best to have it make sense. All right, before we begin, there's a couple really key vocabulary words that we should already know, but I really want to make sure that when you hear me use these words today, that you know exactly what they mean. The first is a population proportion. In fact, that's what this entire unit's about. This entire unit is about trying to decide, trying to find what the true population proportion P is. Now, a population proportion is the true proportion of all individuals in the entire population that fit into a described category. So this would be the proportion of all people who own a Harley Davidson, the proportion of all gummy bears that are green, the proportion of all Skittles that are red. So again, this is a true proportion of all individuals, people, or objects in an entire population that fit into a described category. So coming off of that, that's the number that we're trying to find in this unit. But to find that number, we need a point estimate. A point estimate is simply a sample proportion, which we denote p hat, that is taken from a sample of size n that could be used as an estimate for a population proportion. So the whole point of this entire unit is that we do not know the true population proportion, but we could use our p hat as a point estimate of that population proportion. The idea is that there is one and only one true population proportion. But there are typically, depending on the population, but typically there are millions of p hats. There are tons of different possible sample proportions. And any one of them can be used as a point estimate for what the true population proportion can be. All right, now the other big word that we're going to use a lot is the word interval. That's a pretty basic word. But what is an interval? It is a range of values that represent what the true population parameter could be. So at the end of this video, we're going to be able to generate an interval that has a number at the bottom and a number at the top. And what we want is that this is an interval, again, it's a number to another number, that represents what that true proportion can be. So at the end of the day, I'm sorry, we're never going to be able to tell you exactly what the true population proportion is, but we're hoping we can estimate it with an interval, a value to another value where we believe the truth could fall. All right, so now that you understand those couple key vocabulary words, let's dive into actually reviewing something that we already know. What the heck is a sampling distribution? Now, what I need you to understand at the beginning of this video is that a sampling distribution is an example of deductive reasoning. Deductive reasoning is when you know the truth. You know the truth, and you look for evidence that supports that. An example would be, I read that people have two legs. So I'm going to go out and look at people. Oh, look at Kelly. She's got two legs. Look at David. He's got two legs. Look at Olivia. She's got two legs. So I'm finding evidence that supports what I heard was true. And another example of deductive reasoning could be thought of as, in a criminal investigation, right? If somebody says, hey, I think that Nathan committed a crime. Okay, well, just because one person says Nathan committed the crime doesn't mean Nathan committed the crime. That's not going to, uphold in court, right? So what I need to do as a police officer is if I believe the truth is that Nathan committed the crime, I'm going to find evidence that supports that fact. I'm going to find some DNA evidence, some fingerprint evidence, some forensic evidence, some other eyewitnesses. I'm going to find whatever evidence I can to build my case that points to Nathan being the culprit, okay? So that's deductive reasoning. So a sampling distribution is exactly that. Remember, a sampling distribution starts off with a proportion that we know to be true. So in this case, we know that the true proportion of gummy bears that are red is 22%. Okay, that's the true population parameter. Now what we could do is we could build a sampling distribution to show us what all the millions of possible sample proportions could look like from size 150. So again, the center of the sampling distribution is going to be the truth. The mean of all the millions of p-hats out there is going to be 22%. Now, that is only true provided the condition that the samples are random to avoid bias. Okay, well listen, I know the truth is 22%. The one true number is 22% of gummy bears are red. But again, a sample could be a little higher, a sample could be a little bit lower, so that's where the standard deviation comes into play. So the standard deviation of all those millions of p-hats, again, pretty simple formula we learned last unit, square root of p times 1 minus p, that's the non-red gummy bears, 78%, divided by sample size, and I get my standard deviation. Now, hold on a second. This formula is only true as long as 150 is under 10% of all gummy bears. Pretty sure there's a lot of gummy bears out there, so that we can assume independence between our samples. And then, of course, we can make a picture that's normal. I need to be big enough. So how do I know I'm big enough? Well, 150 gummy bears, 22% are supposed to be red. That number is more than 10. 150 gummy bears, 78% are not red. That number is also more than 10. So I know I'm big enough to be the normal model. Okay, so we have the shape, we have the center, we have the spread. All this tells us what is normal, right? Remember, there is only one true proportion out there. 22% of gummy bears are red. But a sampling distribution shows you the millions of p-hats that are possible. And the cool thing about a sampling distribution is we know the truth, right? We know the truth, deductive reasoning. So we could get a sample. Let's say that we get a sample that comes back at 26%. And we could say, okay, well, does that prove me wrong or does that prove me right? Well, 26% is just a little bit higher. It's not even 2 standard deviations above the mean. So 26% is just a little bit higher. It's totally normal. It doesn't prove anything wrong. In fact, 26% is just, well, hey, samples are going to vary. But if a sample came back unbelievably high, and let's just say that a sample came back at 40%, well, that might alert me to something because this model shows me that 40% is very, very unlikely. So if a sample did come back at 40%, and it truly was a random sample, well, then maybe that would tell me that the 22% was wrong or unjustified. But the point I'm trying to make is this. Sampling distributions is what we've already learned in the past. They're very, very easy. We've spent a lot of time on them. But sampling distributions are like deductive reasoning. We know the truth, so we put it in the center, and the model shows us what is supposed to happen. Let's dive into this a little bit deeper. Okay, so we typically have been saying for a while now that anything unlikely or significant has a probability under 1%. So if I take a look at this sampling distribution that I just made for the proportion of red gummy bears, I know that 98% of samples in the middle are totally normal, right? Only the top 1% or the bottom 1% are significantly high or significantly low. Okay, so these numbers all actually make a lot of sense. The 98% represents 98% of p-hats samples, right? 98% of all the millions of p-hats out there are totally normal. Yes, they might be a little bit more than 22% or even a little bit less than 22%, but they're not weird. They're totally normal. You're only significant if you're in the top 1% or bottom 1%. Again, this is deductive reasoning. Because I could build a sampling distribution based on the truth in the center, I'm allowed to now see what is normal and what is not normal. All right, now let's throw a couple more vocabulary words out you that are going to be very important for this topic. First, the alpha level. The alpha level is the percentage of samples in any sampling distribution that you determine to be significant. So if you are going to look at the top 1% as significant, well, then you have to symmetrically look at the bottom 1% as significantly low. So therefore, my alpha level, and again, the Greek letter alpha looks like that, my alpha level is 2%. And what that means is that I consider 2% of samples to be significant. Okay, so that's a vocabulary word that we're actually going to define on the next slide. But one more vocabulary word that I need you to understand is what's called a critical value. A critical value is a special z-score that I call a z-star. It's not just any old z-score. It's a very special z-score that represent where that top or bottom 1% come from. Okay, so what z-score represents that top 1% or what z-score represents that bottom 1% is known as the z-star, the critical value. It's the boundary between normal and significant. Well, if you've been watching the videos and you've been paying attention, that z-star is 2.3263, and that, because of symmetry, means the bottom is negative 2.3263. Now, I want you to understand where I got that number from real quick, because I did not just make up the number 2.3263 out of my head. So to get that number, we need to utilize invert norm on your TI-84 calculator. So second vars, invert norm is the third thing down. And remember, invert norm wants the area at the bottom. So it wants me to concentrate on the bottom 1%, 0.01. And that is what gives me my z-star of negative 2.3263. But because of symmetry, that means that the top 1% is at positive 2.3263. Okay. So that's where that number came from. So two big vocab words come out of here. First is the alpha value. The alpha level is the percent of samples that we would consider significant. That's the top and the bottom. So don't just say, hey, significance 1%. No. That might be true, but remember there's a top and there's a bottom 1%, so the alpha level would be 2%. And the other important vocab word that you need to know is what we call a critical value. And think of the critical value as the boundary between what's normal and what is significant. And this is a very, very special z-star. And again, you got to use your calculator to find what that is. All right, now, believe it or not, some statisticians actually might want to be more strict. So for example, if I want to be more strict, then I might look at the middle 99% of samples that I'm going to deem normal. Now, if I'm going to deem that 99% of samples are normal, that means 1% of samples are significant. But because of symmetry, that's going to get split up. 0.5% at the top, 0.5% at the bottom. So once again, in this case, my alpha level is 0.01. That's the 1% of samples that are non-normal or significant. And the special z-star, the critical value that marks where those values begin, is positive or negative 2.5758. Now, if you're saying, where did you come up with that number? Use your calculator. I'm only going to do this one more time, and I'm going to expect that you understand it. Second vars, go to invert norm, but it only wants the bottom. So it's going to be the bottom 0.005. That's 0.5%. And that's where we get the negative 2.5758. But remember, because of symmetry, if that's the bottom 0.5%, then the top 0.5% is positive 2.5758. So again, what's going on here? Okay, remember, this is a sampling distribution, right? And our example says we know that 22% of gummy bears are red. So this allows me to say, listen, if a sample comes back in the middle 99% of all samples, it's totally normal. Otherwise, it's a weird significant sample. Again, this is the point of deductive reasoning. I know the truth. The model allows me to see what's normal and what's not. So here's the deal, guys. I'm 99% confident that if you give me a sample of 150 gummy bears, I'm pretty confident that the proportion that are red will be between here and here. I'm 99% confident. If we go back to this picture, in this scenario, I'm 98% confident that if you find a p-hat, a proportion of gummy bears that are red, it's going to be somewhere in that interval. Now, people are even less strict. Crazy, right? But it's possible. So somebody might say, no, you know what? I believe normal to be the middle 95%. Those are normal samples. Now, that means the alpha is 5%. That means 5% of samples are significant. 2.5 at the top, 2.5 at the bottom because of symmetry. So in this case, my critical Z star, again, you could use your calculator to find it, is 1.9600. That, positive or negative. That is the value, that is the cutoff between a low or a high significant value. So in this case, I'm 95% confident that if I get a proportion of gummy bears that are red, I'm 95% confident it's going to be somewhere in that range, okay? And then likewise down here, this is even less strict. 90% is what we're calling normal. I don't actually like this, but some people do it. And this means that my alpha level is 10%. 10% of samples are significant. So in this case, my Z star is going to be the cutoff between the top or the bottom significant. And in this case, it's positive or negative 1.6449. Okay, so let's kind of put this all together. Nice little chart here, right? Kind of throwing a lot of numbers at you. All right, sampling distributions allow me to see all possible samples. And I know that I can be 98% confident. 98% confident means that I determine that the middle 98% of p hats are normal. That means 2% are significant. That puts 1% at the top and the bottom, and that's a critical Z star of 2.3263. And then the chart could also be filled in. And again, some other examples that I just got done going through. For example, if I want to look at normal samples as the middle 95%, that means 5% are significant, 2.5 at the top, 2.5 at the bottom, which gives me a critical Z star of positive or negative 1.9600. Technically, all of these critical Z stars are positive or negative because we could be a high value or we could be a low value. Okay, so again, this is all really, really deductive, right? So if we go all the way back to this picture here, this tells me that, let's see, let's try to figure this out, right? Let's talk about 98% confident. That's a Z star of 2.3263. Okay, so a standard deviation is 0.0338. So if I go 0.0338, whoop, forgot an O there, 0.0338 times 2.3263, that would be a how much I would go up from the mean to determine a really, really high sample. So 0.22 is the middle. If I go up 2.3263 standard deviations, that's going up 0.0786. So the cutoff between a normal sample and a really, really high sample is about 30-ish%, right? Right around 30% or higher would be a really weird high sample. Or again, I could take the 0.22 and I could subtract, because of symmetry, subtract the 0.0786, and this would be a really, really low sample. So anything below about 14% would be a really, really low sample. So the idea is that I could build an interval. A normal sample is anywhere in between 14% and 30%. Anything outside of that would be significantly low. So I'm 98% confident because 98% of samples are between negative and positive 2.3263 standard deviations. I'm 98% confident that if you were to get a sample of gummy bears, I'm 98% confident that the proportion that are red is somewhere between 14 and 30%. That would be normal. Okay. Sorry I've talked so much, but that was all explaining to you deductive reasoning. But the problem is this. If we're going to do deductive reasoning, we need to know the population proportion, and we can see what sample proportions are nearby. We can see the ones that are normally high, normally low, or significantly high, significantly low. But here's the deal, guys. What if we don't know the true proportion? What if the true proportion is what we want to find? Well, then we have to turn to inductive reasoning. Now we want to think through the eyes of inductive reasoning. Inductive reasoning is working backwards, where we do not know the truth, so we have to find evidence to point me in the right direction. So this is like, there's a criminal investigation. The police have literally no idea who did it. No idea. It could be any of a million people. So what they start doing is they look for evidence. They find some fingerprints. Maybe that narrows it down. They find some DNA evidence. They get some eyewitnesses. They get some forensic evidence. And it all narrows it down, and it hopefully points to one person as being the culprit. That's inductive reasoning. So we have no idea, and statistically, we have no idea what the true population proportion is, right? We're clueless. We have no idea what the truth is. So unfortunately, we cannot build a sampling distribution. We can't, right? Because remember, to build a sampling distribution, the mean of all the samples is the truth. Well, we don't know the truth. The standard deviation of all the samples is the truth, p, times 1 minus the truth, p, divided by the sample size. Well, we don't know what the truth is. So, man, we can't build a sampling distribution. But it's super important that you understand that the sampling distribution still exists. Just because we don't know the truth doesn't mean that the sampling distribution doesn't exist. Somewhere out there, the truth does exist. The truth is out there. So the sampling distribution can be built. I just can't build it right now because I don't know what the truth is. All right, so we don't know the population proportion. So all we could do is look at a sample to try to gather some information about what the population proportion may be. Again, it's just like a criminal investigation. We have to start collecting evidence to try to point us in the right direction. So here's an example. The previous example, we knew that 22% of gummy bears were red. Well, now, what proportion are green? I got no idea. So the only thing I can do is take a sample. Get a sample of 150 gummy bears, 57 are green. That is a p-hat of 0.38, 57 out of 150. Okay, here's my hope. I hope that this sample proportion could point me towards the truth. Hence, we call it a point estimate. Okay, now, remember, here's my sampling distribution that I wasn't allowed to build because I didn't know how to build it, because I didn't know the truth. But it does exist. So my p-hat is there somewhere, right? Remember, sampling distribution shows you all p-hats. So my p-hat is in that distribution somewhere. I just don't know where. So the idea is you still have to check the conditions, right? Those 3 conditions that we used last unit, we still got to check. Even though I cannot build the sampling distribution, it does exist. So I still have to assume that the sample is random to avoid bias. I still have to assume that 150 gummy bears is less than 10% of all gummy bears to assume independence between all these samples. And I still have to make sure that I have more than 10 green gummy bears and more than 10 non-green gummy bears. And of course I do. There were 57 green, and there's obviously going to be enough non-green. Okay, so that I can use a normal model. All right, so what do I do next? Okay. So you have to understand that all I did was get a single sample proportion. It by no means is the true population proportion. But here's the deal, guys. Remember, even though I can't build the sampling distribution, I can at least think about it, right? There's nothing wrong with thinking about it. So somewhere out there is the true proportion P. My sample falls, well, I don't know where. I guess it could fall on the high end. It could fall on the low end. It could be a little low. It could be a little high. It could be really high. It could be really low. I just don't know. But here is the key. Think about this for a second. I just got done explaining to you that 98% of samples, remember, sampling distributions show millions of samples. 98% of samples are within 2.3263 standard deviations of the truth. So, if this was a nice, truly good random sample, it should be in the middle. Now, you could always be a naysayer, and I could always have a student say, but Mr. Princheck, it could be one of these high samples. Yes, you're right, it could be. But samples like that are very, very, very unlikely. They shouldn't happen. Or Mr. Princheck, what if that sample's a really, really low one? You're right. Listen, I'm not going to argue with you. It could be. But samples like that are really, really low. So I don't know where my 38% p-hat falls, but my gamble, my level of confidence is that it's in the middle somewhere. Because I know that 98% of samples are in the middle. So I'm not going to worry about the 1% chance that I'm too high or the 1% chance I'm too low. I'm going to worry about the good, the positive. The fact that if this sample was truly random, you know where it should fall? Somewhere in the middle. Okay, so in fact, we are 98% confident that the true proportion is near our sample proportion. That means that the truth is most likely 2.3263 standard deviations of or from our sample proportion. Now, this is where you need to just listen to me for a moment. The truth is in the center. Well, I don't know what that is. But imagine that my sample was right here. Imagine that my 38% was right here. Now, I don't know if it is, but just imagine. If I go fishing, right? And when I go fishing, I don't like to use a fishing line because it's hard to catch a fish with a single line. But imagine if I were to use a net and I were to take my p-hat and I were to cast the net high and low. Then I would assume that the truth will get caught within my net. And look, it did. The truth got caught within my net. And I can play this game all day, guys. What if my sample came back right here, a little on the low end? Well, then when I cast my net down and I cast my net up, once again, I captured the truth. So the idea is that if no matter where my p-hat is, let's just say my p-hat is right here now. If my p-hat was right here and I cast my net up 2.3263 standard deviations and down 2.3263 standard deviations, I should capture the truth within my net. Okay, I'm going to erase all this for a minute. Gosh, I hope you understand that, right? It all comes down to a couple simple ideas. 98% of samples are within 2.3263 standard deviations of the truth. So I'm going to look at that in reverse. That should, in reverse, right? Just think about me flipping that around. That should also mean that I'm 98% confident that the truth is within 2.3263 standard deviations of my sample proportion. If I could take the truth in the center, go up 2.3263, go down 2.3263, and get an interval for where most samples are, I should be able to do the opposite. I should be able to take a p-hat that might be a little high, cast a net 2.3263 standard deviations high, 2.3263 standard deviations low, and within that net should fall the truth. And that is exactly what we want to do, guys and girls. We want to take our sample and we want to first admit to ourselves that it probably is not true. But if we go up and we go down, if we toss a net up and we toss a net down, within that interval, we should be able to capture the truth. So the real question now is, how far do I have to go up? How far do I have to go down to get that value? Well, we run into a problem because I hope through watching this video, you understand that I need to go up and I need to go down 2.3263 standard deviations. But the problem is, what's a standard deviation? Well, here is the formula for a standard deviation. I can't use this formula because I don't know the truth. Remember, the standard deviation formula needs the true proportion P, but I don't know what it is, so unfortunately I can't use this formula. Okay, so we have to create a brand new value called standard error. Don't let the word error have any negative connotation to it, please. It doesn't mean that there's a mistake. It's just called standard error. In fact, we don't even have a symbol for standard error. We just use SE as an abbreviation for standard error. Now, the standard error formula is the twin brother of standard deviation. The only difference is that instead of P, I have to use P hat, the sample proportion. And that is because I don't know the true proportion. Now, this is going to generate a slightly different value than if we knew the truth, but unfortunately, we can't use that formula. So the standard error is it's the same formula, just replacing P with P hat. But because we're replacing P with P hat, we have to give it a new name called standard error. So when we take our sample proportion and we toss a net up and we toss a net down, we have to do it by 2.3263 standard errors instead of standard deviations. So here's what that's going to look like. Think about this. All right, here I am. Okay, so I'm taking my P hat. My P hat was 0.38. And I'm going to go up and I'm going to go down, plus, minus, mathematically, 3.2363 standard errors. And here's the formula for standard error. Again, it's the same formula we've been working with, but instead of P, I don't know it, I'm using 0.38 and the opposite, 0.62, divided by my sample size. So multiply to figure out what that number is, and that's 0.0396. Multiply that by the 2.3263, and I get 0.0921. And we actually have a name for that. That's called the margin of error, ME, margin of error. We'll talk more about that in a moment. So if I take my 0.38 and I go down 0.0921, I get about 29-ish%. And if I go up 0.0921, I get about 47%. So there's an interval. Now, here's the deal. The center of that interval was the truth, 0.38. I cast the net up and down 2.3263 standard errors. So now here's what I can conclude, and I have it bolded and underlined here. 98% confident that the true proportion of green gummy bears, first off, it's not 38%. Sorry, that was just a sample proportion. I'm 98% confident that the true proportion of green gummy bears is somewhere between 28.79% and 47.21%. So the idea going in is I had no idea what proportion of gummy bears were green. My sample revealed 38%, but that's not necessarily the truth. So I went up a little bit, I went down a little bit, and I got myself an interval. Now, I'm not going to lie to you, this interval is pretty wide, but again, it's better than saying 0 to 100%, right? I mean, if you blindly go into it and you say, hey, Sammy, what percent of gummy bears are green? Well, anywhere from 0 to 100%. Okay, well, that's obviously pretty wide. So I was able to narrow it down through this idea to 28 to 47%. Okay, but the idea is that this portion, is really important. What does 98% confident come from? It's this idea that even though I can't make a sampling distribution, I could deduce one. I can envision what one looks like. And the idea is that a sampling distribution shows me where the normal samples fall. And I know that 98% of samples fall within 3.2, I always want to say that wrong, 2.3263 standard deviations. So what I did was I said, well, listen, if I work backwards, I know that the true proportion should fall within 2.3263 standard errors of my sample. All right, so here is a generic formula for what I just did. The name of this is called a one sample Z interval for a proportion. Very long name, but it is important that you know that name. All right, in symbols, all this is your P hat plus or minus your critical Z star times the standard error. Now, the standard error formula is, again, very, very easy. P hat times 1 minus P hat, all divided by sample size inside of a square root. But again, where does the Z star come from? Remember, that's based on how confident you want to be. Typically, we're 98% confident, but as we talked about earlier in this video, you could be 99 or 90 or even 95% confident, and that does change how far you reach for what is normal. All right, guys. I mean, that's pretty much it, right? That's it. It's not overly complicated. Now, the back part, this part back here, has a special name called margin of error. So the margin of error is the back part. It's the Z star times the standard error. Now again, these two formulas are not different. They're exactly the same. All I'm doing is replacing the standard error with its formula, which is again the same formula, standard deviation. So the margin of error is simply how much you're willing to go up and how much you're willing to go down. You probably hear margin of error oftentimes in articles or news reports, because anytime you get a sample proportion, that's not the truth. It's just a sample. But what you do is you go up and you go down by the margin of error, and you get an interval for where you think the truth is. All right. In a nutshell, I'm going to end with this. It takes 4 steps to find a confidence interval. They're all very easy, but you got to do it. The first step is literally just naming what you're doing. A 1 sample Z interval for a proportion. Sorry, that is required in the AP rules. Number 2, you got to check the conditions, because even though I can't build a sampling distribution, I need to understand that 1 does exist. So I have to make sure my sample is random. I have to make sure my sample size is under 10% of the population to assume independence. And I have to make sure I'm big enough with 10 successes and 10 failures. Then I have to do the formula. Guys, the formula requires 3 numbers, P hat, N, and Z star. So doing the actual hard work is so easy as long as you understand where those 3 numbers come from. And then finally, you have to give a nice conclusion in context for what your conclusion or what your interval found. I'm 98% confident the true proportion of blank is in the interval between blank and blank. So for my example that I just did earlier, I'm 98% confident the true proportion of green gummy bears is somewhere between about 28 and 47%. Okay? It's all really, really simple, guys. It's not that complicated, but listen, I encourage you to watch this video again, pause it, read it, listen the second or third time to try to understand all the little pieces and parts. Stay tuned for one more video that follows this one that gives a full walkthrough through an example, so that way you can see how I apply all 4 of these steps to an actual problem.